Hi, welcome to our online physics lab where today we're going to show that acceleration due to gravity on an object is constant. That is, the object accelerates straight down with a constant acceleration due to gravity, which empirically we know is 9.8 meters per second. That is, every second the object gains 9.8 meters per second in its velocity. And we're going to do that quite straightforwardly just by dropping objects and timing how long they take to fall to the ground. So we're going to take a measurement of the initial height of the object, and then we're going to measure how long it takes to fall to the ground. And from those measurements, and by collecting a set of them, we're going to show that the acceleration due to gravity is a constant. So here, let's look at our lab handout. So if acceleration due to gravity is a constant, then these equations that describe the kinetic motion of the object in free fall have to hold for the object. And here they are listed here for us. But in just a second, we'll just go ahead and derive these, just because it's good practice to derive them for ourselves. Then once we have these equations, we're going to show that they describe the kinetics of an object in free fall. So the way we're going to record our data is we're going to check out the free fall motion of several different objects. Here I'm going to use a cannonball just as an example. But when you do the experiment, the objects you're going to be using are first the tank shell, then the baseball, and finally the pumpkin. I'm going to go ahead and use the cannonball just as an example. So we can drop our cannonball from any height we want. And we could fire it here. This thing would fire it with an initial speed. There's 18 meters per second. But in this experiment, we just want to keep our motion in 1D. So I'm going to go ahead and set the speed to 0. If I put the initial speed to 0, you'll see what happens. It's just going to end up dropping the cannonball like that. And here I can drop it from this height of 15 meters. I can drop it from a height of 15 meters all the way down in 1 meter steps, all the way down to a height of 1 meter. And actually notice that the initial angle wouldn't even matter. I could put it at whatever angle I want. The initial speed is 0 and the initial angle won't matter. So here we're going to drop our ball, our cannonball, from this height 15 meters, and then we can measure how long it takes to hit the ground with this multi-tool here. It's got time, range, and height. So it shows us now that at time 1.75 seconds. That's the time between when we fired and when the ball hit the ground. The range is 0 because it didn't go anywhere downrange. And then the height didn't go anywhere down the horizontal, that is. And the height is 0 because when it's on the ground, it's defined to be 0 at a height 0. Up here, the initial height is 15. And notice it doesn't matter. I can change the angle here. And since I'm shooting it with an initial speed of 0, it's just going to fall straight down every time with the same drop time, 1.75. So that doesn't matter, that angle. We say to set it to 0 in the lab handout, and that's fine. You can set it to 0, just a nice comfortable place to set it. And then we can drop for different heights, 14, 13, and so on. Keep going all the way down to 1, final drop from 1, takes 0.45 seconds. So you can see I collected all the data for dropping this cannonball starting from an initial height of 15 meters. So here's the initial height that we dropped it from, 15 meters, took 1.75 seconds like you saw. Then I dropped it from 14 meters, it took 1.69 seconds. All the way down from 1 meter, where you saw it took 0.45 seconds. And here's the data points collected all along the way. And this here is just the trial number, so I just labeled those just for convenience. Didn't really have to, but seemed like a good idea. Here's a plot of the data. We're going to get into that. I'm going to show you how to do that. Okay, so here we plotted the data. Then to that data, we added a trend line, or for that data, we added a trend line. And in this case, we didn't use a linear trend line. That would be a linear trend line. You can see it doesn't really fit the data. But we used a polynomial order 2 And you'll see why we did that as we go on here. Polynomial order 2 trend line, and then displayed equation for the trend line on the chart. We could also display the R value. See, the R value is 1. That means this is basically dead on a second order polynomial being well approximated by this equation right here. But we're not going to have to display that. That's just a little bit of extra information showing how good the fit was. And then now we're going to be able to see that we'll determine the experimental acceleration due to gravity for this is going to be twice the number, twice this 4.8932 number here on the x squared, the coefficient of x squared. So let's get into showing how that works. Alright, so we've seen how to collect our data. To determine if we have constant acceleration due to gravity. And we were using a cannonball as an example. Of course, when you do the lab, you're going to use the tank shell, and the baseball, and the pumpkin. But did the cannon shell as an example. We collected all those data points, time to make the drop versus drop height. And now, from that data, I want to show that we have constant acceleration due to gravity. Okay, so how are we going to do that? Well, for that, we're going to need the equations of motion, the kinetic equations of motion for the object in free fall. Now, they're written down for us on the handout, but let's go ahead and derive them here as practice. And when we have those equations, and those equations are going to be based on the fact we're assuming the acceleration due to gravity is a constant. So we assume that and derive the equations. And then, if those equations match the kinetic description of the motion that we just literally get from Excel by plotting the data, so if the data and the equations match, then that shows us that the acceleration due to gravity indeed is well modeled by those equations, and therefore the acceleration due to gravity needs to be a constant of the value we will find. And the empirical value, of course, is 9.81 meters per second squared. We're going to go ahead and determine that experimentally. Okay, so to do that, first thing let's do is get ourselves a y-axis. Just going to grab a y-axis and think about what happens when I drop a ball. Okay, so one thing I'm going to say, is there's a acceleration due to gravity here, and I'm going to point that straight down. Just going to say that's pointing straight on down, just parallel to this line right here, which is the y-axis. We'll take our ball and start it off from a height here of y0. And I don't necessarily have to assume that it doesn't have any initial velocity right here. It could drop it so that the initial velocity is 0, but could also launch it up, right? Up or down, so it has some initial velocity. Here I'm drawing the arrow up. I'm going to make the up direction positive. So let's just say it has some initial velocity, v0, when we shoot it up. And then later, it's going to be falling down here, and later it's going to come to some height y over here. And when we launch it right here, we're going to launch at initial time t0 equal to 0. That is, we're holding a stopwatch, and when we fire the ball or drop it or throw it up or down, right at the time we do that, we start the clock. So time 0 is equal to 0, and then down here time will be equal to t. Down here, here's the time t, which will be equal to, we can think of the time of flight when we stop our stopwatch. So let's go ahead and see if we can figure out how to analyze this motion. Alright, so let's just start with basics here. So what's the definition for velocity? Definition of velocity is that the velocity is going to be how far you go, delta y, over how long it takes to go there, or the displacement in the y direction over the change in time in the y direction. And so this would be, as usual, would be final minus initial. So here's the final, there's the initial, divided by t minus t0, final minus initial time. But in this case, we start the clock at t0 equals 0, so that's just, and then we can, so that's y minus y0, that's the displacement along the y-axis over the time it takes to make that displacement, t. So now I could solve this if I like for the position y. Now, one thing I have to be careful of right here, so this is in fact true, but I have to take the average velocity. This is the average velocity by definition. The average velocity is defined to be the displacement over the time it takes to make that displacement. So right here, I need to be careful about that, especially for this case, and call that the average velocity. Because the velocity is not constant. The velocity is not constant. It starts off here with an initial velocity v0 and ends up with a final velocity v down here. So when it gets down here, it's going to be coming down this way with a final velocity of v. Now let's say we started by dropping the ball from an initial velocity v0 equals 0. Let's say we did that. And then we let the ball fall for 1 second, let's say. We know that gravity, the acceleration due to gravity empirically that we're looking for, is going to be g. The value of g is 9.8 meters per second squared. That's empirically, which here in this experiment we're planning to show. But you can see that's pretty close to 10. So let's just think of that number as being 10. So what that would tell you is that every second you're going 10 meters per second faster, but in the down direction. So we could say, so for example, let's say if we shot the ball straight up at 10 meters per second. So we shot the ball straight up at 10 meters per second. Then after 1 second, the ball would be going at 0. Why is that? Because so it's straight up at 10 meters per second, but every second the ball is gaining 10 meters per second of velocity, but in the down direction. So it would have started with 10 up, but 1 second later you'd have to add 10 down to that. And 10 up plus 10 down is 0, right? The up velocity, so the same amount up, the same amount is down, you get to 0. Then 1 second later, what would happen? 1 second later, now it would be coming back down, but it would be coming back, when it got to here, it would be going at 10 meters per second once again. But now straight down, right? Because here it would have started at 0. 1 second after that, it would have gained 10 meters per second coming down. And then let's say we now let it fall for another second. So 1 more second. It falls and then falls down to here from y0 to 0. So it started with 10 meters per second going straight down here. A second later, you'd add another 10 meters per second. Now it would be going at 20 meters per second coming straight down here. So let's say in that case, this one was 10 going up. Then when it got down to here, it would be going at 20 meters per second straight down. And we could ask, okay, what would be, let's say we started the clock when it was coming down going this way. So we start the clock when it's coming down at 10 meters per second right here. It's falling, it's gone up there, and then now it's come back down through here, and it's going 10 meters per second straight down, and now I hit my stopwatch and start the time right here. So it's 10 meters per second straight down here, and then down here it's 20 meters per second. What would be the average velocity now between y0 and y in that case? The average would be the velocity that's right in the middle between 10 and 20. Starts here, it's down, going down at 10. Here it's going down at 20. The average velocity would be, in that case, be 15, right in the middle between 10 and 20. Or here, maybe it would be a little simpler to think about it this way. Just think about dropping it from rest. Let v0 equal to 0, so you just let it go from rest right here. So the initial velocity would be 0. 1 second later, when it gets to here, it's added 10 meters per second per second. So 1 second later, it'll be going at 10 meters per second. So what will the average velocity be between here and here? Here it's at 0, here it's at 10. The average velocity would be 5 meters per second. It would be the velocity that's right in the middle between 0 and 10. And this is only exactly true if the acceleration is constant. And in this case, the acceleration definitely is a constant. It's the acceleration due to gravity, which is a constant. Of course, our goal here in this lab is to show that, but suffice it to say that what I was just saying right there was that the average velocity has got to be equal to the average of the initial and final velocity. Like that. That's if you think about what I was doing right there, I was just adding the two together and then dividing by 2 each time to get the average velocity, the one in the middle. Okay, so that's pretty important to know. So if I know if I know the velocities at the endpoints, let's say, that's how I get the average velocity from them. All right, so we might want to put that in there. Well, let's see. Let's go one step further though. Let's leave that right there and then do the definition of acceleration. Let's do the definition of acceleration. So acceleration is defined to be the rate of change of the velocity. The velocity is defined to be the rate of change of the displacement, and the acceleration is defined to be the rate of change of velocity. And here again we have t0 equal to 0, so this is going to mean that delta t is just equal to delta t is t, because t0 is equal to 0. Here we're going to solve for the final velocity in terms of the acceleration. Let's solve for the final velocity in terms of the acceleration. So here we see that's the final velocity in terms of the acceleration. So the final velocity is equal to whatever the initial velocity was plus the acceleration times time. And in this particular case though, the acceleration is due to gravity, and it's g minus g. Minus because it's pointing down. So in this particular case, our velocity is going to be, because the acceleration is minus g. Alright, now I want to get the kinematic equation describing the motion of y, that is, that gives me the position y as a function of time. Well, here it is right here, but I want to eliminate the average velocity. I'm going to want to eliminate the average velocity, and then I'm going to want to eliminate the velocity and just get everything in terms of initial conditions. We want to get it all in terms of the initial conditions. So here we have y is equal to y0. Okay, y0 is an initial condition. That's, say, the drop height. For example, 15 meters or 13 meters. Whatever height we launch the ball at. Or drop it. That's the first thing we were doing with the cannonball, just dropping it. In that case, the initial velocity is 0. v0 equals 0. Okay, so that's one initial thing here, and then we have, okay, then it's plus the average velocity times time. But here I'm going to put the average velocity in this form. Okay, so that's definitely the case there. Now what I want to do though is I want to get everything in terms of initial conditions. So I want to eliminate the velocity v here in terms of this equation right here, because here this is just an initial condition, that's the initial velocity, and here's the constant acceleration due to gravity, and that's what we're trying to show right here in this lab, that this is a constant. So I'm just going to substitute this here, the right hand side of the equation, which is equal to v, into v for this term right here. So I just substituted v0 minus gt in for v into this equation over here. So you see that's all that happened there. And so you see what you got. So inside the parentheses here, we've got 2 v0s. So on top here, I've got 2 v0s. v0 plus v0 is 2 v0s, but that's going to get divided by 2. So we're still going to have y0. So from those two terms, I'm going to have 2 v0s divided by 2. That's just a v0, and that's times t. v0 times t. Take a minute if you need to show that this expression here can be written as this expression for y down here. Just a reduction, so we'll see that y is equal to y0 plus v0t minus 1/2 gt squared, and that's the equation for the position y as a function of time and the initial conditions and gravity. This is the expression we were looking for all along. So we collected all the data with our cannonball. Here we dropped it from a height of 15 meters. It took 1.75 seconds to hit the ground. Then we dropped it from 14 meters and it took 1.69, and so on, all the way down to 1 meter. We dropped it and it took 0.45 seconds to hit the ground. Each time I'm saying we dropped it, right? Well, what's the initial speed? You can look over here, you see the initial speed is 0. So let's look at what our equations of motions are going to tell us in that case, and how we can use those with our data. So here we have our equations of motions that we want to use with our initial data. So here's this particular case here that we're talking about. The initial velocity is 0. So if the initial velocity is 0, our equation describing the position, the y position, at any given time t after we drop the cannonball is going to be y is equal to whatever the starting height is. This term is 0, v0 is equal to 0, so there's nothing there for that, so minus 1/2 should be 1/2 gt squared. Okay, so here's our equation. Let's look over and see here what we're collecting data for. If you look at the data we're collecting, what do we got? We got our initial drop height and the time it takes to hit the ground. Alright, our initial drop height, time it takes to hit the ground. Okay, so what is t going to represent in this equation here if we're thinking of that being the time it takes to hit the ground? Alright, so in the next part of this exercise, what we need to do is think of t being the time of flight. Let's let t be the time of flight. That is, t is the time it takes from when we drop the ball, the cannonball, to when it hits the ground. When that's the time of flight, we can ask, okay, well, what's y right after y at the time of flight, and then, of course, right after the time of flight. Y will stay the same after that. Can you see over here? Let's have a peek. When the ball hits the ground, what height is it at? 0. Y is equal to 0 at t is equal to the time of flight. And forever after that. But then those equations of motions don't apply any longer, because then y is just quite simply 0 forever and ever at any time beyond 1.75 seconds, as you can see. So when t is equal to time of flight, here at 15 meters dropping it, 1.75 seconds is that time of flight. But whatever that is, y will be equal to 0 when that happens. So in this equation here, we consider that, and then this equation becomes 0 is equal to y0 minus 1/2 gt squared. So I'm just going to write this equation this way. I'll just write it like this. This is equal to 0 is equal to minus 1/2 gt squared plus y0. And now here, to get this equation to correspond to what we're going to plot in Excel, if you look over here, what we're plotting in Excel is the initial drop height as a function of time. That's what I've plotted right here, these data points. These data points correspond to, here in so the y value here on the vertical axis is the initial drop height versus the time of flight on the horizontal axis. So come back over to this equation, and we'll just solve it for y0. It's practically done for us right here. Just move the minus gt squared over to the left-hand side of the equation. Or we could just write it like this. Initial drop height is equal to 1/2 gt squared. That's a second order polynomial equation. If we look over at the handout, we can see right here, this is a second order polynomial equation. Here it would be of the form y0 is equal to ax squared plus bx plus c. Ax squared plus bx plus c is just a polynomial of order 2. So if we think about that over here, just a polynomial of order 2. Let's just think of, I'm going to write it as y0 because, for obvious reasons, I think, because we're thinking about y0. So here there's times and not x's, but let's just start off this way because from algebra we may be familiar with this as a polynomial equation, second order polynomial. And let's see if we can match it up with this guy here. So here we have 1/2 gt squared, and then, I could say, plus 0 plus 0. Okay, so now we could say, okay, what terms correspond to what in the second order polynomial? We can see that here x has to play the role of t. X normally in physics I think of as the horizontal axis, but here it's just the unknown in a polynomial equation, and that polynomial equation is really in terms of t. So I'll just set, okay, so x goes to t, and what would a be? In this case, you can see a has to be equal to 1/2 g. A is 1/2 g in this polynomial equation. So I'll just do one last step here. One last step would be that the g we're looking for if we knew what A was for whatever reason, then the G we're looking for will be twice. The G, the acceleration due to gravity we're looking for, is twice the A. You can just see from the definition for A right over here. All right, let's look at how we can use this idea and the power of Excel to help us experimentally determine our acceleration due to gravity. So here's a spreadsheet where I already did this exercise, and I found the experimentally determined acceleration due to gravity was 2a, and here a would be the 4.8932. So down here what I did is to get this experimental value, I just multiplied 2 times 4.8932 to get my experimentally determined acceleration due to gravity, which matches the empirically known acceleration due to gravity, 9.81, by 2%. Get it? So right here is just the discrepancy as a percent. Just the known value minus the found value divided by the known value expressed as a percent. Okay, well, let's see, how did I do that? So collecting the data points, that's pretty straightforward. I think everyone can manage that. Just record the initial heights and then the time of flight, the drop time it takes when you drop from that initial height. Do them for all the possible heights you can. Here there's 15 of them because you start from an initial height of 15 meters and go down to 1. So let's see how we would go ahead and plot that. How did I plot that? So to plot it, I could just select all this data right here, and in this case I have my horizontal axis values go on the left hand side, and then the vertical axis values go, or the y values go on the right hand side. And when you have your data formatted like that in Excel, that's, I think of as the natural format for your data points in Excel to plot. Then you could just go over to Insert, Scatter. I like the scatter plot one, and click on it. There's a scatter plot. So now I just replotted that data. And when I did it the first time, I added a chart title and I did axis. Here how you could do that if you wanted to is go to Chart Elements. Here you could click so chart title. You click on that, it's already got one. Or I could get rid of it, maybe. My chart title. I can do axis titles, and I can format them. Like for example, this one here, I could go, okay, it's Y0, and I'm measuring it in meters. Very important to include units. I can do this or not do it as I choose. In this case, I'm choosing to do it. Here we could call this time of flight. I'm just going to call it T. I know what time. I know that T is the time of flight. So I'll just leave it as T. And chart title. Maybe I'll just call it versus time of flight. Something like that. And so here's all our data points right there plotted. Now, those data points should correspond to this equation right here. Y is equal to 1/2 gt squared if the acceleration due to gravity is a constant. And if it is, then all our derivation above has to hold. So that's what we're assuming is true. So if that's true, then that equation right there should be the equation that describes all this data. Okay, so let's see what we're going to do then. So now we're going to add a trend line. Okay, so we're going to do add trend line. And there's the linear trend line. So we go, okay, look at the linear trend line. Well, what we had there was not a linear equation. So it was a second order polynomial equation. So we're going to select that one. We're going to select polynomial. Here we could change the order around. Okay, got an order 3, 2, 1, whatever it looks like. But here, of course, we want order 2. And set intercept, we're going to set intercept to 0 because I know for a fact, we can just look back over at the equation if we like. Look back over the equation, and you see when t is equal to 0 times 0, what is y0 supposed to be? 0. Okay, put t equal to 0, and then so that means that there's no drop time at all. So for there to be no drop time at all, what's your drop height? 0. So that's why we select set intercept. That means that when t is equal to 0, we want y to be equal to 0. Set intercept to 0. Okay, great. And then display equation on chart. We definitely want that because that's what's going to give us the information we're interested in that we're going to use to calculate the acceleration due to gravity. So now we've displayed our equation on the chart, and you can notice what this equation is. So it's y is equal to 4. So now you see the equation for our trend line is y is equal to 4.8932 x squared minus the small number times x. So in a perfect world of perfect data collection, this small number should in principle be 0 because there is no first order term in our polynomial equation. Go back and look at the equation, you'll see there was only the second order term. Right here, x is playing the role of t. There was no minus some constant times t term. There was only a constant times t squared term. So x is playing the role of t. Here y is playing the role of y0. And according to that equation, this is 1/2 of g. 4.892 is 1/2 of g. So what's g? G is twice that. So it's 2 times 4.893 experimentally with a discrepancy of 0.2%. So that's the first part of the experiment done with the cannonball. Then the next part of the experiment is to repeat it but shoot the cannonball straight down. And we'll do that just to verify that the acceleration due to gravity doesn't depend on an initial velocity. Seems like maybe it's obviously true, but let's be sure it's true since we can do so experimentally. And it'll give us, by the way, another data point for our data collection of experimentally determined values of acceleration due to gravity. It's good to collect as many data points as you can, or as many determine the acceleration due to gravity based on as many different experimental runs as you can, because that's going to provide you with a way to calculate the uncertainty of the experiment and also help you verify that the experiment is correct. Our goal is to show that the acceleration due to gravity is constant, independent of an object's mass or independent of what kind of object you use in the experiment. So the acceleration due to gravity on any object, it should be a constant 9.8 meters per second squared, independent of what the object is, what its mass is, or any other thing like that. It's just a constant for all objects. And that's true. Of course, you go, okay, if I drop a feather, why is that feather all of a sudden falling slower than a lead ball? Well, it's because of air resistance. The lead ball experiences much less air resistance. The feather experiences a lot of air resistance. But if you get rid of air resistance, and you can do this if you have a vacuum chamber, you can drop the lead ball and the feather in a vacuum chamber, and you'll see that they both fall exactly the same rate. For each projectile, this lab also asks us to collect a set of data where we fire the projectile straight down. So to do that, you can just take your cannon, turn it straight down at an angle of minus 90 degrees, set the initial speed to 5 meters per second, and then we'll fire it straight down at 5 meters per second. And then we're going to collect our data just like before. We're going to start from our initial height of 15 and then go all the way down to a final height in steps of 1 meter. You take data point at every 1 meter step down. To the last data point you can take is at a height of 4 meters. And you can't go any lower than that because you have to tilt the cannon to a different angle besides minus 90 to go any lower than that, because the cannon takes up some space on the vertical there. So we get to collect a few less data points in this case. And now there's going to be an initial velocity of our projectile. It's going to be minus 5 meters per second. It's minus 5 because the minus means we're shooting straight down. If we shot it straight up, it'd be 5. Here's minus 5 means we shoot straight down. So that means that this V0 in this equation here is minus 5. So we collect all our data points as before, just fire it. These are the initial heights. This is the time of flight, which you just measure with this tool right here, this time range height tool. Get your time of flight for each initial drop height. We plot that data on a spreadsheet. Again, that data is a second order polynomial trend line. And here, why is that? Well, again, so this is the time of flight. That's the time it takes to hit the ground. So when it hits the ground, okay, when we think of t being the time of flight, what is the height y? This equation tracks your height y for all times from time 0 to where it hits the ground. At the time it hits the ground, this term y, what this whole thing is equal to, is 0. So all this stuff here, y0 plus v0t minus 1/2 gt squared, that's all 0 when t is the time of flight. So solve it for the initial height, and you get the initial height y0 is equal to 1/2 gt squared minus v0t, just coming right out of this equation. And that is the equation that corresponds to the equation of our trend line. So when you do the trend line, do second order polynomial fit trend line. Again, you can set the intercept to 0 on the trend line, because when t is equal to 0, then this whole thing should be equal to 0. This is the equation of your trend line, so we'll see what these terms correspond to. This 4.992, that's corresponding to 1/2 g. This 4.8947, that's corresponding to minus v0. Okay, minus v0. Why is this one plus and this is minus? That's because this term is actually minus 5. So a minus times a minus is a plus. So this term here, in a perfect world, this would actually be 5 instead of 4.8947, such that it's not 5 for the initial speed is 5. That represents some error. Down here we've collected our experimental results where we can compare it with theory. So here's the theoretical value we're looking for. Gravity is 9.81 meters per second squared. And the initial velocity, we know we set that to be minus 5 meters per second. Experimentally, we got gravity is just twice this number here. It turns out to be 9.984. And compare that with the theoretical known value down here as a percent. So how do you do that? Just take the known value minus this value we got divided by the known value, and you get minus 2%. Why is it minus? Well, it's minus because this one's bigger. If I take this one and subtract this one, I'll get a minus sign. So that's all that minus means in the percent discrepancy. And here, look at over here, so here we know it's minus a minus. So this is telling us that experimentally our initial velocity straight down was 4.89947, or 4.9, and that's 2% different than minus 5. So here I have a second experimental value that was known that we can check the error on, the experimental error. Okay, so we do that. So we did that for the tank shell. We did the tank shell just dropping from Freefall up here. So here's where we dropped it from Freefall, collected our data for that. The initial velocity was 0. Then we did the experiment again, where we shot it straight down, just turn it down to angle minus 90 degrees, shoot it down at 5 meters per second, collect our data for that. So we can do that for each projectile. You're going to do that for your 3 projectiles right here, tank shell, baseball, and pumpkin. That's going to give us 6 data points, or 6 results of the experimentally determined acceleration due to gravity. And we can go ahead and get the average of those results and take that as our experimental result. And since we have a quorum, we have 5 or more data points. Here I got 6 data points, and these aren't the same as the data points you're going to get, but I have these here just so you can see how to do the calculation. So you just take the average of all these with Excel, just type equals average and get that. Standard deviation, you put that's the standard deviation of all these right here. The standard error is the standard deviation divided by the square root of the number of data points. That's 0.2. The discrepancy from theory, here again you just compare with 9.81. So 9.81 minus 9.525 divided by 9.81 is going to give you 3%. And now we can write our final experimental result in the proper form of best guess plus or minus uncertainty. So our best guess in this case is 9.5 plus or minus uncertainty here, 0.2. We can see how this 0.2 is driving the precision, the significance. And here we can see our uncertainty. This is our uncertainty. If we add the 0.2, then we would have got 9.7. That's even a little off the 9.8. So our results aren't even within, the uncertainty is not bounded by if you add the uncertainty, what I'm trying to say is, when you add the uncertainty, that doesn't take you all the way up to 9.81. So even including our uncertainty, the bounds of our results lie just a little bit outside theory, and we're just a little beneath it. Does this make sense, considering we turned the error resistance on, that could be the case? I think if you think about that for a second, you'll think, well, yeah, that might make sense. Error resistance would tend to slow things down, and so we would probably get a result that's slightly less than the real result for the acceleration due to gravity. And that is the case here. So if you turn the error resistance off, I think you'd find something a little different happens. Last, you want to verify that the acceleration due to gravity is independent of the object's mass. So to do that, take something like the tank shell, for example. That definitely ignores air resistance pretty well. And then especially if you turn the air resistance off, then everything ignores air resistance, so everything should shoot the same in that case. Then you can toggle the mass around, change the mass from low to high values of mass. Try shooting the same object. It's the exact same object. It has the exact same volume and shape and size, but it just changes its mass. So you fire it and see if that affects the motion of the projectile. See what you find out. What do you think you should find? See what you get, and see if that shows that the acceleration due to gravity is independent of an object's mass. Okay, so that's everything you need to do for the experiment. Try to have fun with it. Enjoy it as best you can. You can turn everything you need to turn into me. It can just be included with your spreadsheet. You can answer this question on your spreadsheet. Include all these statistical analysis, just like I show here. Include all those on your spreadsheet, just as we did in the handout here. Your data should be a little different, but see what you get. Then you can either email me your completed spreadsheet or include it as a submission in Blackboard for me there. Okay, I'll see you in the next lab.